Hello everyone. Welcome to the online lecture series on engineering physics. In today's session, we are going to discuss the important topic from quantum mechanics, which is the particle in one-dimensional rigid box, which is also known as particle in a one-dimensional infinite potential well. Let's consider a one-dimensional box of length L whose walls are at x equal to 0 and at x equal to L. The potential at the wall is infinite as well as outside these two walls is infinite. So therefore this one-dimensional box divides this space into three regions. A region 1 which is of infinite potential, and region 3 again which is of infinite potential, and the region 2 is the region of box where the particle is there inside this one-dimensional box, and this particle will be represented by a wave function psi of x. Let's consider a case of a free particle for which its potential energy is 0. Now, mathematically, we can represent this case of one-dimensional rigid box, means a particle in a case of one-dimensional rigid box. Here, the potential energy V will be 0 inside the box for which the value of x will be in between 0 to L, and the value of the potential will be infinite at the wall as well as outside the walls in region 1 and region 3, for which the value of x are either equal to or smaller than 0 or either equal to or greater than L. Now here in this case, as the potential energy is independent on time, we can use Schrodinger's time independent wave equation to get the solution of this particular problem. The Schrodinger's time independent wave equation can be written as d2 by dx square of psi of x plus twice m times total energy minus the potential energy divided by h cross square times psi of x equal to 0. So this equation 1 represents the Schrodinger's time independent wave equation. Now if we use this Schrodinger's time independent wave equation, or if we are applying this Schrodinger's time independent wave equation for the free particle confined in a one-dimensional rigid box whose potential energy is 0, then let's substitute V as 0 in this time independent wave equation. Therefore, this equation becomes d2 by dx square of psi of x plus twice m e by h cross square psi of x equal to 0. Now in this equation 2, if we make a substitution for this particular term, which is this twice m e by h cross square as some quantities square, suppose a phi square, then this particular equation will be reduced to the form, and that form is d2 by dx square of psi plus phi square psi of x equal to 0. If you observe this equation 4, then this will be the second order differential equation in psi, which is equivalent to the case of simple harmonic oscillator, whose general solutions can be expressed as a sine function or a cosine function. So therefore, the most general solution of this particular equation can be written as psi of x equal to a times sine of phi x plus b times sine of phi x, where these a and b in this particular equation are known as arbitrary constants. This constant can assume any values, and we can find out their values by using the boundary condition. Now the boundary conditions of this particle are which are at x equal to 0 and at x equal to L, where the wave function psi of x becomes 0. Now if we use this boundary condition, it means as we substitute x as 0 in psi of x, then the psi of x becomes 0. Therefore, from the solution equation, which is the equation of psi of x, that is a sin phi x plus b cos phi x, let's substitute x as 0, then this psi becomes 0. So therefore 0 equal to a times sine of phi x, it means sine 0, plus b times cos of phi x means cos 0. Now here as sine 0 is 0, so this term becomes 0. Therefore we get the value of one of the arbitrary constant, that is b, which is equal to 0. Now by substituting the value of b as 0 in the general solution, now the general solution becomes psi of x as a times sine of phi x, as the term containing b becomes 0. Now if we consider a second boundary which is at x equal to L, again at x equal to L, the wave function psi of x becomes 0. So therefore in this equation, when we set x as L, this psi of x becomes 0. So therefore 0 equal to a times sine of phi x, it means phi into L. But here we have to understand that this a in the equation of psi of x should not be equal to 0. If this a itself is 0, then the psi of x becomes 0. Whatever be the value of x, the psi of x itself becomes 0 if the value of a is 0. So that's why this a should not be equal to 0. Then this implies that this sine of phi L must be equal to 0. And now if sine of phi L is equal to 0, this indicates that the value of phi into L must be equal to n pi. Only then its sign comes out to be 0. Therefore phi comes out to be n pi by L. In the general solution, we can substitute the value of n pi by L in place of phi, and hence the general solution or the wave function psi of x becomes a into sine n pi x by L, provided that this n should not be equal to 0. If n is 0, then for any values of x, this term itself becomes 0, and as sine 0, this psi of x becomes 0. Means the wave function will vanish, and hence this n should not be equal to 0, and it can assume all possible values starting from 1 onwards, 1, 2, 3, 4, like that. It means this n is a set of natural number. To find out the possible energies of the particle, let's consider the substitution term this phi square for twice me by h cross square, and just now we have find out the equation for this phi as n pi by L, and hence if we square that equation 7, then we get phi square equal to n square pi square by L square. Now from these two equations, phi square as twice m times e by h cross square and this phi square as n square pi square by L square, we get that is twice m e by h cross square equal to n square pi square by L square. Now from this equation, the nth state energy of the particle will be given by this term n square pi square. Now take this h cross square to this side, it is multiplied here by h cross square divided by, after taking this twice m to this side, it becomes twice m times L square. And now if we substitute for this h cross as h by 2 pi, we get the nth state energy of the particle as n square h square by 8 ml square, provided that this n should not be equal to 0 and it can assume all possible values starting from 1 onwards, that is 1, 2, 3, 4, etc. This energy equation gives us all possible energy of the particle which is confined in a one-dimensional rigid box. Now depending upon the value of this n, if n is equal to 1, then this corresponds to the ground state of the particle, and the corresponding ground state energy will be represented by E1. Now from this equation, if we substitute n as 1, we get E1 equal to 1 square times h square by 8 ml square, that is h square by 8 ml square. This represents the ground state energy of the particle, the lowest possible energy of this particle, which is also known as 0 point energy. Now from this equation 11 and this nth state energy of the particle, we can express this En as n square times h square by 8 ml square, whereas this term h square by 8 ml square is the ground state energy from equation 11, and hence we can express this En as n square times E1. So this clearly indicates that the possible energies of the particle will be either E1 or n square multiple of E1. Now if we consider the value of n as 2, then the particle is said to be in its first excited state, and the corresponding energy of that first excited state will be given by E2 equal to 2 square times E1, which is 4E1. In the same way, if the particle is there in the second excited state, then the value of n will be, then the value of this n will be equal to 3, and its second excited state energy will be given by E3 equal to this 3 square times E1, which is 9E1. And if it is in third excited state, which corresponds to n equal to 4, then E4 comes out to be 16 times E1, and so on. So that is how we can find out all possible energies of this particular particle which is confined inside a one-dimensional rigid box. Thus it is very much clear that the allowed energies of the particles will be either E1 or n square times E1, whereas the energy values which are in between E1 and 4 times E1, like these are the various discrete energy states of the particle, the allowed energy levels. Either it will be even, 4 times even, 9 times even, or 16 times even. But now if you observe that the energy values in between this 4 times even and even, which are like 3 times even, 2.5 times even, 2 times even, and so on, all these energies are known as forbidden energies, or we can say that those energies are not allowed by the particle which is confined inside a one-dimensional rigid box. So therefore, here also in between these 4 times even and 9 times even, there will be a number of energy values which are not allowed by the particle. And hence, we can conclude that in quantum mechanics, for a given quantum mechanical system, either it will be going to be possesses a lowest possible energy, that minimum energy of the system is known as its ground state, or some suitable multiple of that minimum energies will be the allowed energies for given system. Whereas the rest of the energy values are known as forbidden energies. This is exactly in contradiction to the laws of classical mechanics. As per the laws of classical mechanics, a classical system can assume any values of energies right from 0 value to its maximum value. So no forbidden energy concept is there in case of classical mechanics. Now moving on to the next important part of this particle confined inside a rigid box is its wave function, or its nth state wave function, which represents the possible quantum states of the particle, and also we are interested to find out the probability density functions for the particle. So for that, let's recall the general solution equation, that is the equation number 8, which was psi n of x is equal to this a times sine of n pi x by L. As we know that a quantum mechanical wave function must satisfy the 4 important conditions, like that it must be a single valued function, it must be a finite function, a quantum mechanical wave function must be a normalizable function, and at the same time the wave function as well as all its first order derivatives must be a continuous function. So therefore, here we need to normalize this psi n of x by using a normalization condition. So therefore, the equation of normalization condition for this case of particle confined in a one-dimensional rigid box will be what? It is the integration of psi n star x into psi n of x, which represents the probability density. It means the complex conjugate of psi with the psi into this length element dx gives the probability value. This term is a probability density, means probability per unit length multiplied by length element is the probability. Now the integration of all such probability for all region of the one-dimensional box where x varies from 0 to L, then the integrations of all these probability elements is going to result into 1. This probability will be 100%. So this equation number 13 is known as the normalization condition. Now by using this normalization condition, we can normalize this wave function psi n of x. Now here, as there are no imaginary terms or imaginary units are present in this psi n of x, so therefore its complex conjugate means psi n star of x will be the same function as that of this psi n of x. So therefore the product of the complex conjugate of this psi with the psi will simply be its square, a square and this sine square. So therefore from this normalization condition we get this as mod a square into this integral where the x varies over 0 to L sine square of n pi x by L dx, that is going to be equal to 1. As here the higher power of trigonometric ratio, the second power, is involved, to solve the integrations usually we convert the higher powers of trigonometric functions into the one power. Then by using this particular identity, the sine square theta can be expressed as 1 minus cos of 2 theta divided by 2. We can simplify this term of sine square n pi x by L. Therefore, this equation will take the form mod a square into integral over x varies from 0 to L. Now the sine square n pi x by L term can be rewritten as 1 minus cosine of 2 times this n pi x by L divided by 2 into dx equal to 1. Now if we common out this 1 by 2 from the integration, then it becomes mod a square by 2. Now inside the bracket, let's separate out the integral for the individual term. So we get integration of this 1 dx minus the integration of this cos 2n pi x by L dx, where the limit of x varies from 0 to L, that is equal to 1. This becomes mod a square by 2. The integration of 1 with respect to dx is x, the limit of x are from 0 to L, minus, and the integration of cosine is sine. So cos of 2n pi x by L will be sine of 2n pi x by L divided by the derivative of this function, which is 2n pi by L. And the limits of x varies from 0 to L, that is going to be equal to 1. Now let's substitute the upper limit and the lower limit of x. We get mod a square by 2 equal to this. When we substitute upper limit, then it becomes L, lower limit, then it becomes 0. So this term becomes L minus 0 minus. Whenever we replace this x with L, LL will get cancelled. It becomes sine 2n pi, which comes out to be 0. And even if we substitute the lower limit as x is 0, this term itself becomes 0 and sine of 0 is 0. So therefore in both the cases, while substituting the value of upper limit and lower limit for x, this sine term becomes 0, and hence this will result into 0 minus 0. And this bracket is completed, and that is going to be equal to 1. Now we can express this as mod a square by 2 times L equal to 1, and hence this mod a square comes out to be 2 by L. It comes out to be 2 by L, and hence the value of a will be root 2 by L. This value of a is known as the normalization constant. Now upon substituting its value in the wave function, then the sine of x becomes, now a will be replaced with this, a can be replaced with this root 2 by L into sine of this n pi x by L. This represents the normalized wave function and it indicates the nth state of the particle confined inside a one-dimensional rigid box. So psi n of x value is this one, which is there in this equation number 17. And if we try to find out the probability density value function, then we have to take the mod psi square for this state function. Then this mod psi n of x square comes out to be the square of the square root term. It means it is 2 by L times the square of this sine function. It is sine square n pi x by L. So this equation number 18 is the equation for probability density function of the particle. Now depending upon the value of n as 1, 2, 3, correspondingly we get the different quantum states of the particle. When n is 1, we get the ground state, and if the value of n is 2, it corresponds to the first excited state, and if n is 3, it represents the second excited state of the particle. Now, these first three state functions and the probability density functions for the particle confined inside a one-dimensional rigid box will be given by these equations, which are the ground state wave function will be given as psi 1 of x is equal to root 2 by L times sine of 1 times pi x by L, and the corresponding probability density for the ground state wave function will be this mod of psi 1 of x square is going to be equal to 2 by L times sine square pi x by L. For the first excited state, that first excited state function psi 2x will be root 2 by L sine of, now n becomes 2, it is 2 pi x by L. Corresponding probability density value will be mod psi 2 of x square will be 2 by L times sine square 2 times pi x by L. And for the second excited state, that state function is represented as psi 3 of x. It would be under root 2 by L sine of 3 pi x by L, and the corresponding probability density function would be psi 3 of x square, mod psi 3 of x square will be 2 by L times sine square of 3 times pi x by L. Now it is interesting to see that how these state functions varies as a function of x and the probability density functions varies as a function of x for this case of particle confined in a one-dimensional rigid box. Let's consider the case of state function first. Now, the first three quantum states of the particles are represented by this psi 1x, psi 2x and psi 3x, which are ground state, first excited state and the second excited state. Now inside the box whose walls are at x equal to 0 and at x equal to L, then the psi 1 of x, which corresponds to root 2 by L. Now from these equations, you have to recall these equations, root 2 by L times sine of pi x by L. Now it depending upon the value of x. If x is 0, sine is 0, so the value of psi 1 of x is 0, right? If x is 0, the value of psi 1 of x is 0, and if x is L, again the value of psi 1 of x is 0, but at x equal to L by 2, the term pi x by L takes the form pi by 2 and sine of pi by 2 comes out to be plus 1, and hence we get the maximum value, which is root 2 by L for the ground state function. So it varies like this. If the particle is there in the first excited state, now then the sine function we'll take this form under root 2 by L as the sine of 2 times pi x by L. Now here, as x varies as 0, L by 2 and L, the value of sine function 2 pi x by L comes out to be 0. But for the value of x as L by 4 and 3L by 4, the value of sine 2 pi x by L comes out to be plus 1 for x as L by 4, and its value comes out to be minus 1 for x as 3L by 4. And corresponding wave functions can be represented like this. Here simply we have divided this length L into 4 equal parts. So the one part is L by 4, this two parts is 2 times L by 4, this is 3 times L by 4, and the last one would be 4 times L by 4, which is 4, and so on. If the particle is there in the second excited state, then the corresponding state function would be this one, root 2 by L times sine of 3 pi x by L. Now 3 pi x by L, for that, if we divide this total L into 6 equal parts, first part is L by 6, this could be 2L by 6, comes out to be L by 3, this is 3L by 6, comes out to be L by 2, this is 4L by 6, comes out to be 2L by 3, this could be 5L by 6, and the last one could be 6L by 6, comes out to be L. If we divide this total length of the box into 6 equal parts, then for these different values of x, the value of psi 3 of x, specifically the sine term, sine of 3 pi x by L, then at this L by 6, the value of sine comes out to be positive. At L by 2, the value of sine comes out to be sine 3 pi x by L comes out to be negative, and at 5L by 6, for the value of x as 5L by 6, the value of sine function sine of 3 pi x by L comes out to be positive. Whereas at x equal to 0, at x equal to L by 3, again at x equal to 2L by 3, and at x equal to L, the value of psi 3 of x comes out to be 0. So that's why if the particle is there in the second excited state, then that second excited state wave function will behave like this. These are the plots of the quantum mechanical wave functions of the particle confined inside a one-dimensional rigid box. Now let's consider these probability density functions for the same three states, like the ground state, first excited state, and the second excited state. If you carefully observe these probability density functions, then in comparison with these wave functions or the quantum states functions, here you can notice a difference that this is just the square of this function. So root 2 by L becomes 2 by L, and now the square of this sine function is sine square of the same value, 1 times pi x by L for ground state, 2 times pi x by L for first excited state, 3 times pi x by L for second excited state, right? Only the difference is that here there is the square of this sine function. As we know that the value of sine can varies from -1 to +1. While taking the square, the minus values of the sine also becomes plus. So therefore, if we plot these three probability density functions of the particle confined inside a one-dimensional rigid box, then here in this quantum states functions, the possible change would be what? The negative part of these sine functions will becomes the positive. While taking the square, the -1 value becomes positive. The same thing happens to this curve. It also becomes the positive for these second excited state functions. And at the same time, here the amplitude was root 2 by L. Now in probability density, its square would be 2 by L. So the amplitudes will be little bit more. In all cases, the amplitudes will be the little bit more as compared to these quantum states functions. and at the same time these negative portions will appear as a positive in the probability density function. So therefore the plots for the probability density functions will look like this. These are the plots for the probability density functions for the particle confined inside a one-dimensional rigid box for ground state, first excited state and the second excited state. At these different intervals, at these different values of x, the ground state probability density functions will vary like this. Its amplitude will be maximum at x equal to L by 2. But if the particle is there in the first excited state, now at L by 2, the probability density comes out to be 0. And its value will be maximum at these two positions, at the two values of x, which corresponds to the L by 4 position and 3L by 4 positions. When the particle is there in the second excited state, now the probability density values are maximum at x equal to L by 6, at x equal to L by 2 and at x equal to 5L by 6. Whereas the probability values will be 0 at x equal to 0, at x equal to L by 3, at x equal to 2L by 3 and at x equal to L. This clearly indicates that in quantum mechanics, the probability of finding the particle at different position inside a one-dimensional box or inside a uniform region is different. This clearly indicates that if the particle is there in the first excited state, then that particle will be most likely to be found out at the middle of the box. But if the same particle is there in its first excited state, now at the middle of box, you cannot find that particle. It will be most likely to be found out at the L by 4 position and at 3L by 4 position. Again, if the particle is there in the second excited state, it would be most likely to be found out at L by 6, L by 2 and 5L by 6 as we get the maximum amplitude of the probability density function. This clearly indicates that the probability of finding the particle at different places would be different. Whereas in case of classical mechanics, if the space or the region inside this 1D box is homogeneous or same everywhere, then the probability of finding the particle at different positions would always be same. Anywhere inside the box would always be same. This is as per the laws of classical mechanics. But from these probability density plots, we can clearly conclude that the probability of finding the particle at different positions inside this one-dimensional box is going to be different. So this is about the energy values and the possible quantum states of the particle and the probability density functions of the particle which is confined inside a one-dimensional rigid box, or it is also known as inside an infinite potential well. So thank you very much.